Welcome, and today we're going to look at what is the force created by fluid, and we're going to look at one direct application, which is the manometer, which basically is an instrument used to measure the pressure. Okay, so let's first look at force created by a fluid. So in order to explain this, let me just consider a tube, a pipe, that we're going to fill with a certain amount of water. Okay, so let's say initially we just fill up to that line. So agree with me that then the specific weight or the specific gravity of the water is going to create some weight on a membrane over here, and that membrane will have to withstand whatever force or weight is created by the fluid. So obviously the more fluid you have, the bigger that force. So let's say the tube is filled with water, so you will have here gravity rho g, and you know that the amount of the force will depend on the amount of water you put within your tube, so on the height of the tube. But this could be just the height h of your tube. But obviously also the force will depend on what? On what is the diameter of your tube. So this will be equal to rho g h a, and that is the force that would be observed by the bottom of the tube, by the force F over here. So if we just apply the basic static equation, summation of force equal to 0, you will find out what? That, okay, and let's say positive is going up, find out that F minus rho g h times A is equal to 0, or that the force created by the fluid is equal to what? Rho g h times A. Now, if you recall what is the definition of pressure, it is force over area. So that means that the force is equal to the pressure times the area. So basically what this term over here is really pressure. Okay, this is the force, and this will be the area. Okay, so just to add one quick thing to the force created, so using this, it will be logical then that let's say we have a similar tube over here, but this time we selected to fill this tube with different fluids. So let's say here you have a fluid ρ1 that goes to a change in height h1. You have a 7 fluid over here with a density of ρ2, h2, and let's say finally you have a third one over here, h3, with density H3, you can easily see that then applying again the static equation, positive up, that the total force should be equal to what? Rho 1 G H1 plus rho 2 G H2 plus rho 3 G H3. Okay. Okay. So let's go to the first application, which will be to look at the manometer. So the manometer is generally a container that contains some type of gas. So let's say it will be P gas. And then there is a tube generally with a U shape. Okay, so you want to measure whatever is in here. And let's say this is open to the atmosphere. And for the first case, I'm going to do the simple case. Imagine that the pressure of the gas needs to be equal to the surrounding pressure. So in this case, there is no change in pressure. So let's say we fill this with water. So then how should be the water? The water should be level on both sides. Okay? So let's say we take an element of the fluid. We could take this one, but you could have taken another one here or here, doesn't matter, it's anywhere. Whatever happens within the fluid, the same thing happens everywhere. So let's say I'm going to sketch that one. So if I go and sketch that element of fluid over here, what do we have? Okay, so on this side will be the top, you will have P gas. Oh, and on this side you will have P atmosphere, but I'm missing one thing here. See that this will be our reference line, okay? So you see there's no change between either one of them, okay? So if we apply our summation of forces, again, equal to 0, this will give us minus P gas times A plus P atmosphere times A equal to 0, which will give us that the pressure of the gas is equal to the pressure of the atmosphere, which is what we were expecting, since that was our assumption. So I'm doing this because now we're going to go and study the more general case in which, let's say, we're going to have a manometer, the same one as before. So again, you have here P gas and here P atmosphere. So this time, let's say this is our reference level. So let's say I go from, instead I'm going to go from here, and there's a change in height that goes up to here. Okay, so basically there's a change here of level equal to H1. So which pressure will be higher, P gas or P atmosphere in this case? So will be this side of the tube or that one. So in order to study this case, let us break this into two parts, at least for the understanding. Then we will not be doing this every single time. So first, we're going to do a figure in which we're going to show what would happen if the system was in equilibrium. So basically that P gas was equal to P atmosphere, and the reason of doing this is so that we can use this line over here as our reference line. Okay, and now I'm just going to be doing exactly the same figure over here. With P gas, P atmosphere. But this time, let's say the fluid is going to go down 1 letter square, so it should come up 1 up. All right. So again, what I'm going to do is that I would like to take the same element that we had before. Could be any one. Let's say this one for clarity. So what happened to that element? So we go from here. So basically we are here, here. So we take the same element. So what do we find out over here? This is our element. It was up here, and now it went down here. So at this side, we're still going to have P gas. But now, what needs to happen on this side? We're still going to have our P atmosphere, but to send it back to the equilibrium position. And what do you need to think about equilibrium position? Because what is the equation we use all the time? Newton's equilibrium equation. What needs to happen? We need to P atmosphere. Now we need to move this up by the fluid rho g times the change in height h1, that will be this height over here. Okay, so now you can apply the static equation that will tell you what? Minus P gas times A plus P atmospheric A plus rho G H1A, all this should be equal to 0. So if I cancel out the area on each term, you end up with minus P gas plus P atmospheric plus rho G H1 equal to 0, which will give you that P gas will be equal to what? P atmospheric plus rho G H1. Okay, so after doing this case over here, now let's do the other one where if you want the fluid will go down on this side or this one will go up. So in this case, let's just follow exactly the same steps. So let's say we have here our manometer. Right, so P gas, P atmosphere, and this time we say that what we actually want is the fluid to go up, and let's say to stay down on this side. So this time there's a change in height H1 this way. Okay, so again we're going to do exactly the same thing. Figure when the system is in equilibrium in order to get a reference line, well, really a reference element. Okay, so P atmospheric, P atmospheric, P gas, P gas. So if everything was in equilibrium, let's say it would be here. Okay, and now we say this is going to go up, so it's going to go down over here. So we are here. This will be the change in height. And again, our reference line is over here. So like before, let's say our reference element will be this one. So now what happened to our reference element? So our reference element will be this one here. So this time the element went up, which means that this time we have like the void or the empty space will be at the bottom. So it will run up this, say the element, this will be the empty one. Okay? So the element went up. So what will be our reference line? Reference line is over here. Okay, so if you want to look at this element here, will be the same as this one. Maybe here you need to look more at this element. It will be easier to understand. Okay, that went through it. So on this side, what needs to happen over here now? So we know we're going to have here the P gas, but to move this element to the reference line so that we can use the static equation, which is summation of forces equal to 0, we need to move it to the state over here. Okay, so we need to move this one down. Okay, we need to push this one so that this element can go up. So by how much we need to push it? Plus rho g h1, where h1 is that height over here. And then on this side, you will still have the P atmosphere acting at the reference line. So by doing so, what do we have? P atmosphere times A minus P gas times A minus rho g h1 times A equal to 0. By now, you should see that we can cancel the area. This will give you what? P atmosphere minus P gas minus rho g h1, which will give you that the P gas will be equal to what? P atmosphere minus rho g H1. Okay. All right, so let us try to summarize the results. To try to come up with a procedure that will help us to solve the problems a lot faster. So in this case, let's see, if we have the case, the first one, so our first case, if this is our reference line, we had that the fluid was under the reference line and was going up the same amount on the other side. So let's say this will be P gas, P atmosphere. So in this case, we derive the equation P gas equal P atmospheric plus rho g H1. On the second case, I do a similar pipe. With P gas and P atmospheric, and let's say this will be our reference line. So this time we want the fluid to go down on this side and up on this side. Okay, so here, let's see, the liquid went up H1, and in this case, the liquid went down H1. And for this case, we had that P gas was equal to P atmosphere minus rho g H1. Okay? So let's try to come up with some type of rule over here. Let's say this side will be the initial, I, and it will be final. It will be the initial, this will be the final. So, if the change between the initial and the final, so basically if change between initial and final position of the fluid. So we say that position final higher than position initial, you need to add the rho GH, whatever the fluid is doing. So this is with respect to the reference line, okay? Higher with respect to the reference line. If the position, if the final position is lower than the initial position, let's say you need to subtract rho GH. Okay? So on the next video, I'm going to do a manometer, but for multiple fluids, in order to test these conclusions that we draw over here.